Well, it's official, folks. It's now week 10. Welcome back, everyone. So with what we've got going on this week, we'll have quiz 7 due on Thursday. This one's going to be based off the chapter 7 problems. So see either the 2 examples here or the extra example for a guide on how to get through those, or the one on quiz 7. And the next big thing we're going to be doing is working in chapter 13. The big goal of the course is inferential statistics, which is chapters 13, 14, and 15. We're going to go through these carefully and methodically. They're pretty abstract sections, but it should feel like kind of the same kind of stuff we've been doing all along, whether it's constructing a box plot from scratch using the 1.5 IQR rule of thumb, or the formulas at the end of chapter 3. It's all the same kind of stuff. We just practice how things go, work with the context on making conclusions, and other ideas of identifying population versus sample, parameter versus statistic. We still have to finish off chapter 10, so that's going to be a kind of a good refresher before we start 13.1. But any questions at the moment, folks, before we begin? Okay, well, here's where we left off last Thursday. Right before example 4, we're looking into the difference between the dichotomy of parameter versus statistic, as well as the sample versus the population. Population is everything that we want to study, all the individuals or all the objects collected into one group. The sample is what we actually study. And when it comes to the parameter, we've seen a few. Let's list this out again as kind of a warm-up. Parameter, or sometimes called a population characteristic. I'll just say parameter because it's shorter. Well, I like that word, population characteristic, because that's what a parameter does, is it describes the entire population. In chapter 6, we used parameters a lot. We were describing populations with a normal curve. So we saw things like these examples. Mu and sigma were the population's mean and standard deviation. The new example we're going to study a lot in chapter 13 is going to be P. So let's define this one here. P is going to be the true proportion or the population proportion. The population proportion of something. I'll just leave it population proportion. Proportion of the thing we want to study, whatever it might be. P hat is going to describe the sample, but it'll be the sample proportion. But before just jumping into that, these are all the parameters. And the big idea with the statistics is, in most settings, these are typically unknown. With some very rare exceptions, like on the last example, we actually had a census available to us. And that was one of the reasons we actually knew the value of the parameter P. But censuses are sometimes extremely costly or just impossible to calculate. And so we use the statistic. Statistics that we've seen so far in this class have been Y bar, really the same order that we saw here. Y bar estimates mu. S is the sample standard deviation, which estimates sigma, the population standard deviation. And the statistic we'll study in chapter 13 that goes along with P is P hat, the sample proportion. Once we actually calculate the sample, all of these are known values. So that's just kind of a roundup of the parameters versus the statistics. Not all of the statistics we've seen, but the major ones we're going to be taking a look at. And just to practice this one more time, here's the new example with a new context. Any questions at the moment with the parameters versus the statistics? Okay, so here's some pretty old data. It's over 50 years old, from 1974. It says to evaluate the routine policy of vaccination of infants for the whooping cough, adverse reactions were monitored in 339 infants who received their first injection of the vaccine. So this is back when this was a brand new vaccine, it looks like. Reactions were noted in 20.35% of the infants. So here's that study where this was published, the Lancet, in 1974. So the big question for us is, do the 339 infants represent the population, or did this represent the sample? Anyone see which one this would be? Yeah, absolutely. We could say it's a sample because if it was the population, well, that would mean the 339 infants count as all infants back in 1974. Maybe that could be true for maybe a small town, but this seems to be a pretty big study, looking for the big impacts of it in an entire nation at minimum. So we can say here, the 339 infants is a sample because the population is larger than 339 in this problem. So we have a sample size of 339. Our common way we wrote that in was n equals 339 infants. And we have the value here, 20.35%. So at this point, we want to decide, is 20.35% a parameter or is it a statistic? Yeah, absolutely. The moment we said the 339 infants count as a sample, we can come back up here. A statistic describes a sample, so this value is in fact p hat. So absolutely right, we can say here, using the symbol just as a way to start to learn this symbol, we'll use it more and more. P hat equals 20.35 is a statistic because it describes the sample of 339, which was in infants. And I think that's it for the notes. We did it, folks. That's the entirety of chapter 10. Really, we're just talking about these ideas, statistic versus parameter, population versus sample, in another more very close way. And another part of the notes in chapter 10 was looking into what kind of conclusions you can make in statistics, depending on if you had an experiment or an observational study. Well, we're about ready to turn into chapter 13. I want to pen in just a few more takeaway ideas for things that we're about to see a little bit more and more of. When it comes to this thing, population proportion and sample proportion, we can say P equals the population proportion of successes. So that's the new thing here. Let me highlight that a little bit, underlying it in purple. So that would be the full description of what P is. Likewise, when we say P hat is the sample proportion, we mean the sample proportion of successes. Another thing that kind of is a good reminder is whenever you write out that symbol, this is read as P dash hat. So if you hear me say P hat, that's what I'm referring to. That's thought of as a hat, I guess. So everyone started calling it P hat. So that begs the question, what do we mean by a success? A success is the part of the study that we are actually interested in studying fundamentally. And looks like I might have typed a number on that. A success is not always a good thing, like the language might specify. It's just what the study is all about. And this problem, when they told us reactions were noted in 20.35% of the infants, that was p hat, and we're saying of the 339, this is the percentage. I should have thrown in the percent symbol there. Let me throw that in. That's the percentage of the sample that was a success. It sounds kind of awful, but success is adverse reaction to the first injection of the vaccine, only because that's what they're studying in this problem. So let's say here, just to tie in the concept, a success is an adverse reaction to the vaccine. So these are the ideas we're going to carry forward into chapter 13. Our goal is to estimate p hat. Excuse me, our goal is to estimate p. Let me write that in just so we can get that idea for sure. Our goal is to estimate p using the fact that it's approximately equal to p hat. So that's going to be the goal of chapter 13, to talk a little bit more about that approximation. Well, any questions at the moment? Okay, we kind of looked into this problem briefly because it's such a large problem for this course. Really, we're on week 10. We have quite a bit more to go, but the rest of the course is all about these kind of ideas. Inferential statistics in this way, or maybe inferential statistics in this way, that the unknown mu is approximately equal to y bar, but we run into one critical problem where these are decent estimates. They're unbiased. They're really nice in a certain sense, but we have to do a little bit more. We have to describe what is the error in making that estimate. We can't do that, then in a certain sense, they're useless estimates for us. And for another context where this came up, this was our notes all the way back in the first day of class. We looked in a different kind of population, all San Fernando Valley residents, and we want to study the population proportion, the parameter p, which was going to be the proportion of residents okay with the transit tax. We needed a random sample, so we hope we have a nice random sample that represents all San Fernando Valley residents. We said it was 100 people in the sample. And so the statistic, p hat, is going to be the sample's proportion of successes. But a success here is being okay with the transit tax. That was the major thing that they wanted to study. For just a quick example, p hat is going to be the number of successes, 56, divided by the sample size, so it came out as 0.56. And so we can come back over here and say the population proportion is approximately 56%, or 0.56 if we prefer the proportion. But that's the issue. That's an approximation. And everybody needs to know what is the reliability in that approximation? What is its margin of error? How well can we trust it? This is what chapter 13 is all about, describing this approximation a little bit more thoroughly. In fact, what we're going to give is a whole interval of numbers that p is likely to be in with a certain level of confidence, say 95% confidence or even higher. So this is where chapter 13 starts. And to make this estimate happen, we actually need the normal distribution, which is completely unexpected. It seems like it comes out of nowhere, especially because this is categorical data. We took the 100 residents, they're in two categories. You're either in okay with the tax, that's one category for successes. There's another category that was the people not okay with the tax, the failures. So this is categorical data. Yet we're going to use a tool for quantitative data, the normal distribution, to model it and describe that error. So it's a tall task in chapter 13. And let's jump over to it just to see how it goes. First, any question of looking into this idea one more time? Okay, so this course was super, super fast tracked. We would have gone from chapter 1 to chapter 6 to chapter 13. But everything we did in the middle is important, describing what the statistics are, how to compute with them. Chapter 3 was really more about probabilities, and so is chapter 6. And when we go to give this interval, we'll be thinking in terms of probabilities. All the conclusions we give, we're just thinking about the context, and we've been doing that all along when we were describing what we see in graphs. So now finally, let's close these notes and go over to that chapter 13. Once it saves, there it goes. It starts off with just a collection of all the definitions that we've been looking into, because we do have new parameters and new statistics we're talking about. So to just redefine those two major ideas, the individual or object that possesses the characteristic of interest, whether it's an adverse reaction to a vaccine or being okay with a new policy like the transit tax, that's going to be called the success in the sample. Something that does not possess the characteristic is the failure, but If the study is focusing on the successes, so are we. This means already, this is categorical data with specifically 2 outcomes. Feels limited, but it's a not too bad of extension to go to 3 outcomes and beyond in later parts of the book. So let's just mention right here, this means we have categorical data. In the later chapters, chapter 15, we'll get into the quantitative data, but this means we have categorical data, 2 outcomes, which are successes, or let's just say success, failure, are those 2 outcomes. So the statistic we use to make the estimate from the sample is p hat, the sample proportion of successes, and this is how it's calculated. We take the number of the successes you find in the sample, divide by the sample size n. So n is entering in our formulas once again, n is our sample size. So p hat is a statistic because it describes a sample. And we relate that to the population proportion p. Let me just highlight up to p hat to include it there. P is the parameter since it describes the actual population that we're going to study. So we have the sample proportion p hat, the population proportion p, much like we had y bar, the sample mean, versus mu, the population's mean. But the major formula is this one in the middle. Once we know what a success is and what the sample size is, we can calculate p hat. We'll be doing that in some of these problems. So this sets up the problem, but the major task of example 1 is also going to be seeing how the normal distribution enters into the problem. So here's our new context, just a short one. It says, from USA Today, once again, 2010, the article Facebook Etiquette at Work reported that 56% of people, and this is 15 years ago, so that's probably a different number, but 56% of people participating in a survey of social network users said it was not okay for someone to friend his or her boss. That's a pretty interesting statistic. I wonder if it's gone up or down. For full disclosure, I don't think it's okay to friend my boss, Patrick Ralt. That would be really weird. And it goes on to say, let P denote the true proportion of all social networks that feel this way. And suppose that, just for the sake of a problem, P equals 0.56. Well, that's doing the idea of we took the data, P hat is 56%. Let me color code that a little bit better. The 56% of people participating in the survey is p hat. We make an assumption. We say, suppose p is 0.56. We're not saying the true proportion of successes is really 0.56. We're just making this estimate. Suppose it really came out as p. Well, along the way of doing this, we have to say what is a success and a failure in this situation. The success in this problem is, well, the thing we're trying to study. If 56% say, or 56% of the people participating in the survey or the sample itself said it was not okay for someone to friend his or her boss, that's the success of the problem, saying it's not okay to be your boss's friend on social media. So we'll say here, a success is saying it is not okay to friend, whatever that might mean on a social media platform, the boss. So that's what the success is. Then it said 56% of the people participating in the study said it was not okay to friend their boss. That means the p hat over here was the 56% or the 0.56 if we wrote it as a proportion. We also have to say what the failure is, so let's say that as well. A failure is saying it is okay to friend the boss. So we have a success and a failure in this situation. We're making a huge assumption that P is a 0.56 and going from there. Well, part A is really just thinking about the parts of how you compute P hat, how you might relate it to a parameter. Any questions about the successes or failures there in part A? Okay, here's where it starts to get pretty abstract. This is why chapter 13 is kind of a hard one to start. But once we're at the end of chapter 13, actually computing the confidence intervals, it's not so bad. So it's one of those chapters that's hard to understand, but once you get that under your belt, it's not hard to use the chapter. It's weird because the TI-84, which has been a trusty tool, and it'll continue to be so, it kind of fails at this part. We're looking into a pretty big concept about the so-called sampling distribution and sampling variability. So it poses kind of a hard question. Part B can never be a real quiz or exam question. It's mostly all about exploring these two pretty technical definitions. So let's take our time with it. Part B asks the question, would P hat, based on a random sample of 50 social network users, have a sampling distribution that's approximately normal? Use a simulation to address this question, and that's what we'll do in class. So the TI-84 can't quite do that part for us. We need to describe what do we even mean by a sampling distribution. That's this definition, but it relies on this idea here, the prior definition. So let's go through carefully with this technical definition. Any quantity whatsoever calculated from the sample is called a statistic. So here, 56% of the people participating in the study said it was not okay to friend their boss. That's the statistic, P hat. So we labeled it using that terminology. So we know what the statistic is, but here's the issue. This study was done once with one particular sample. I don't know what the sample size was. Let's suppose it was 50 based on part B. If they rerun the study, say they did it twice in 2010, they reran the study again with a different random sample, 50 different people, they're going to get a different P hat value because the data is random. P hat is not going to be the same every single time. They're probably all going to be close within a certain amount, but they change, they fluctuate. And that's the so-called sampling variability. Same idea is true with the sample mean Y bar. Every time we do a study with quantitative data, and we calculate the average, that average depended on the random sample. Rerun the study again, and you get a different random sample, you get a different sample mean. So your statistics, they all vary. The only thing that's tacked down, that's nailed to the ground, that doesn't vary, is the parameter P, but that's the unknown. We're just saying, supposing for the sake of the example, it takes on a specific value that we know, 0.56. So the observed value of statistic varies from sample to sample, depending on what's selected. And this is what is known as sampling variability. So we do a kind of thought experiment. These are experiments that can be done in real life, but they would be costly. Let's say, repeat the study, repeat this study. Let's say we had the budget 100 times. Well, the study gave us one P hat, 0.56 or 56%. But if we repeat this study 100 different times, we're almost guaranteed to get 100 different values of this statistic. And they're all going to truly be different. If the sample's different, almost guaranteed, so is the statistic. If they came out exactly equal, that would be like an anomaly in a real sense. So repeat the study 100 times, we get 100 different values for P hat. Let's call them, say, P hat 1, P hat 2, so on. There's 100 of them, so we don't want to be typing these forever. But then p hat 99, and the last one, p hat 100. They're all numerical results, right? They're all proportions. They're probably all pretty close to each other. All of them are estimating p. This is a good statistic, so they're all trying to get close to the same exact thing. And you know what we can do with 100 different values is put them into a histogram. No one's going to stop us. So we can construct a histogram of these values. And we wonder at this stage, what would that histogram look like? Is it skewed to the right? Is it skewed to the left? Is it bimodal? Or is it unimodal? Is the mode close to p, the true unknown thing we want to calculate? Is it highly symmetric? What are the features of this histogram? And this is a feature of every study involving p hat, and the same for every study involving y bar. Either statistic will have this feature. You could have repeated that study if you had the budget and the man force many times, not just 100, maybe 1,000, maybe 100,000 times. The distribution you get, there's exactly one of them, formed by the values of the sample statistic for every possible different sample of the given size is the sampling distribution. It's an abstract thing, so there's lots of ways to think about it. You can think about imagining repeating the study, getting 100 different p hat values, or you can simulate it, and that's what we're going to do. We're going to actually simulate this process of calculating 100 different p hats, or maybe even more, maybe 1,000,000 of them. Why not? If the technology can do 100, it can do 1,000,000. We'll see what happens when we put them into a histogram and what that histogram actually looks like. Before we jump into that, any questions at the moment? Okay, so this is the big idea in statistics, that you can take a statistic like p hat or y bar, that's just in the later chapters, and relate it with some totally new distribution called the sampling distribution. So to do that, here's the part of the notes where, let's hope that comes back, where we're going to use a bigger calculator just so we can visualize stuff. This is not something I'm going to ask you to do for the course. It's kind of like whenever we pull up Excel. It's just for the sake of a demonstration. While it loads, let's take a quick mental break. It was ready to go, but I just learned today this will sign you out if you leave it idle for too long. Okay, so we're looking at some weird stuff here. Imagine it's a TID4 just with a lot more features. Let me show you line by line just what we're doing here. Let's hide that stuff for the moment. So we have the value of the population proportion P. I'm going to state P as 0.56. And that comes from the problem here in 13.1. Let me minimize this just a little bit. We're in 13.1, we said, suppose P is 0.56. So we made that assumption right here. So that's the population proportion P. Then we said, suppose we're going to deal with p hat based off 50 social network users. So we can do something kind of amazing. We can simulate what would happen here. If the true success rate is 56% or 0.56, this next line is going to simulate the sampling distribution of p hat. This is like doing a study exactly once. Let me clear this out. So if I run all of this, my p hat value supposed to be somewhere here. P hat came out as, hang on, let me try one more time. And let me close that. Sorry, I practiced with this earlier, but seemed to have forgotten everything I was about to do with it. Or like starting from here. So if the true proportion is 56%, we have a sample of size 50. This is going to simulate getting the successes out of there, saying it's okay to friend your boss. Now let me hit Control Z, enter on just that. one more time. There's the button I want. So I have the successes, that's p hat, and it came out to 0.5. A little bit off of this, so half of my sample was 0.5. Let me just type out p hat again. If we repeat this just one more time, got to use this button, it came out as 0.46 because that's just a different random sample. So this is R for random. Binomial distribution is just where the successes come from. And every time I run this, I get a different p hat value out. This one came out really high at 62%. And that can happen with statistics. If the true parameter is 56%, but you go to take a random sample, even at size 50, it's not completely accurate. That was the main thing we were complaining about at the very start of chapter 1 on week 1. That's the statistic p hat is not exactly the parameter. We have to describe the error. Run it again, it's at 0.6. Again at 0.68 on the high end. 0.58, that time it came close, but that was just the luck of the draw on that. We increase the sample size, we hope that it's even more accurate. Let's just see if that happens. Let's suppose we take a sample size of 500,000 social network users. We'll calculate the number of successes that emerges in the sample, divide by the sample size, and really, really close to 0.56 now. If you round, it is 0.56 to 2 decimal places. Run it again. It's 0.56 if you round this to 2 decimal places. It's not as close as before, but the higher the sample size, the more accurate the statistic. But that's the problem with statistics. I can't run a sample at size 500,000 because that's too costly. USA Today or whoever did the study probably doesn't have the budget. So they reduce it to size 50. So let me see if I can control Z back to this point. So when this is a 1, this is just doing the study one time. But like we mentioned in the notes, we want to know what happens if you repeat the study a whole bunch of times. So let's put here 100. Clear that out again. If we repeat the study 100 different times, we're going to get 100 different values of p hat altogether. Then, like we mentioned in the notes, you can put all of those into one big histogram. So now this is 100 different p hats all in one spot. The histogram that I build is just this stuff down below. It's going to put all the p hat values, the statistics, into a table, create a histogram through this syntax. And finally, this is what I was trying to run at the very start. Here's what you get. It's kind of messy, right? But that's a histogram, like we said. All those p hat values went inside here, and we put 100 of them in one spot. Kind of strange, kind of jagged, but notice the true value is supposed to be 0.56. Most of our p hat values are right around here, just above 0.56. Some of them are on the high end, some of them are on the very low end, but that's kind of rare, it looks like. These look like single counts or maybe twos. But if you run this again, get 100 different random samples, the picture changes. Now it looks like this. Now this time, on these next 100 samples we got, imagine we repeat the study 100 times, looks like most of them, 17 maybe, ended up here. So seem to be slightly biased that time. None of these are the exact sampling distribution. The sampling distribution is every possible different sample that could ever emerge from the given sample size of 50. We can't do every possible sample necessarily with the technology, but we can approximate that. Instead of 100, power 3 is 1,000. Let's just write it in, it's simpler to see. If we repeat the study 1,000 times, here's what happens next. Sampling distribution takes on a slightly different shape. Starting to get this mound shape, and the peak looks like it's more likely to be right at 0.56, between the 0.54 and the 0.58. Do the study in USA Today 10,000 times. Takes on a more suggestive shape. starting to look like the normal distribution. Would you all agree with that statement? It's kind of striking in a way. The true value of the parameter is 0.56. That's about what's in the middle right here. There seems to be a peak. It falls off in a nice predictive way. It's unimodal. It looks like it's highly symmetric and bell-shaped. And just to see if the technology can handle this, let's go up to 1,000,000 different times. This is our best effort of actually showing the sampling distribution by showing many different possible samples all at once. 1,000,000 different samples. It's kind of an amazing calculator in a way. So this is 1,000,000 samples. Instead of a bar plot, let's call this a histogram, just so that it feels a little bit more similar to what we're saying. It is using the bar plot code here, but when you put space 0, it becomes a histogram. So Control A, Control Shift, and here's our histogram of the sampling distribution. It's, again, really, really striking. These are all the possible values of p hat. Well, maybe not quite all. The technology can't go forever, but we ran this 1,000,000 times, and this is a pretty good approximation. So let me try to get my windows back in order. There we go. So the question was, would p hat, based on a sample of 50 social network users, have a sampling distribution that's approximately normal? Let's put this on the next page. And based on everyone's reactions, we can say, yes, we're looking at a normal distribution. And that's kind of phenomenal because now chapter 6 is back on the table for us. Excuse me, chapter 5, the standard distribution and the normal model. So this takes a nice, clean, normal distribution shape. My hand is a little bit unsteady, but you can imagine that's about what it would look like. The normal distribution has an amazing feature. The thing that we want to estimate is the direct center of this. So this is p, 0.56. That just says the statistic is doing a pretty good job. The statistic is centered right at the thing you want to estimate. The hard thing about this, however, is the center, the mean of the normal distribution is not the full story. We also have to describe how spread out it is. If we can say how spread out it is, that's the entire statement of what it's going to be called the central limit theorem, the biggest idea in inferential statistics. But here, the simulation is showing us that the central limit theorem is plausible. We get these shapes. Any questions at the moment with these ideas? Okay, let's peek at the central limit theorem and then come back to this. The reason we didn't just skip to the central limit theorem is because it's saying a lot. It's really abstract. The general properties of the sampling distribution of p hat. You go to do a study where there's successes and failures. You have one population, all the people you're studying, but then there's a second population that is under the ordinary one. It's where your actual statistic p hat comes from. The statistic p hat is going to be the proportion of successes in the random sample. And it turns out the mean of the sampling distribution is the unknown parameter p, the thing we want to estimate. The standard deviation is this complicated object here, square root of p times q divided by n, where q is 1 minus p. But rule 3 is the major thing. When n is large and p is not too near the numbers 0 or 1, the sampling distribution of p hat is approximately normal. That's the thing we're looking at in the simulation. The normal model has mean or center at the parameter p, and standard deviation, that's formula there. We need to investigate, what do we mean by n is large? You have to say what you mean by that. And what do we mean by p is not too near 0 or 1? We never say what we mean about that either, then we still have a problem with this. And so that's going to be our second look in the central limit theorem in these notes here, saying what these two parts mean. But so far, the central limit theorem is kind of a paraphrase of what we were just looking at. we need to look into these ideas as well. Well, let's take a look into the last part C. Suppose, just for the sake of seeing what can go wrong, that the true population proportion of successes is 0.93, say close to 1. For this sampling distribution, we had a sample size n was 50. And a new question is, approximately how large of a sample is needed for the distribution of p hat to be approximately normal again, just like in this problem? So p hat came from here somewhere. But if you change something about the problem, if p is too close to 0 or 1, or n is not large enough, this picture vanishes once again. So let's pull up that simulation and see what's going to potentially happen. We're making a change. Instead of saying the true proportion is 56%, we're going to say 93%. That would mean in our problem, 93% of social network users say it's not okay to friend his or her boss. So go to 93%. And let's actually drop the sample size to 5 and just see what happens as we increase it. The sample size is just 5, and we repeat that sample a million times. That's what this part is all about. Here's what the approximate sampling distribution would look like. We get that picture. Notice how wide the bars are. It's because if their sample size is 5, there's actually not a lot of things that can happen in your sample. You have these possible values, 0, 0.2, 0.4, 0.6, 0.8, or 1. 1 occurs a lot. Must be just because the true success rate is close to 100%. 0.8 occurs a lot, and these values don't seem to occur at all in this run, even when we made it happen a million times. Or maybe it's just too thin of a slice to see, like how 0.4 is really thin to see as well. So that doesn't look good, right? We want to use essential limit theorem, which says there's a normal distribution here. But on that picture, the normal distribution has nothing to do with heavily skewed distributions, like this left skewed one. But if you increase the sample size, let's say from 5 to 25, so a 5 times increase, here's the new effect. It's still skewed, right? But something really weird happened. This is the central limit theorem in action. When the sample size got larger, 25 social network users, we calculate the successes in a sample size of 25. Sampling distribution is still skewed, but not as much. A peak emerges here. It falls to the left quite a lot, and a little bit to the right. So now we wonder what happens at 50. Take a sample of 50 users, and the skew is coming off little by little. Still, you would say this is left skewed, I would say. You could kind of fit a normal curve to here, but it's not a good fit. It's not like when we looked at it over here. When it was 0.56, the sample size of 50 was great, right? It was almost perfectly symmetric. That's just because the thing we were trying to estimate was close to the middle. And that's what the central limit theorem is saying. We have big problems when p is too near 0 or too near 1. N has to be large to overcome those issues. So we're bumping up the sample size. Studies with categorical data sometimes are not cheap, especially if you're studying something that happens almost all the time or something that's a very rare condition. Let's bump this to a sample size of 100. At sample size 100, you kind of improve, but not by a lot, right? It still has just a little bit of a skew to the left. We're trying to estimate something that's at 0.93%. Here's our main peak. It's doing a good job there, but if we try to use a normal distribution, it's just not quite dead on what we would like. Let's keep on going. Let me know the point at which you feel like this looks like a nice normal distribution, much like how this one looked like a nice normal distribution. Size 150. That's a pretty large sample already. How would you folks feel about this? Is this large enough? Some say yay, others for yay, or do some say a little bit larger? looking at it so far, we have these rectangles here, which seem to conflate with these rectangles here, and just a little bit trailing. How about we do a compromise and just go up one more level, sample size 200. But I would agree at this level, it looks really very symmetric. The error in putting a normal curve to these data is not that much off at all. Sample size 200 looks like this, cleaned up, but just by a little bit, right? So here's our distribution. If you look at this carefully, this is the part that seems to be further off than this part over here. It still skews to the left. In fact, there's always left skew. The only way to take it out of there is if you go ridiculous and then the skew to the left is imperceptible. Let's see if the computer can run this. Looks like some instability actually happened here. These little spikes wouldn't be real, but the symmetry looks pretty profound at a sample size that's in, I didn't even count this off, that's looks like 20 million. No one's going to do that sample. That's just way too prohibitive. But at 200, that doesn't look too bad. A sample size of 200 is probably going to give us pretty accurate results. What we need is a better rule of thumb. We don't want to pull up a crazy calculator every single time we're deciding it is large enough. So after we get through the next example, we'll see a good rule of thumb for determining when is a sample size large enough to handle when n is at the p is at the extreme, close to 0 or 1. But just to finalize this question, here's the last graphic. Again, this is a pretty crazy calculator. We won't open it again for the rest of class. But hey, if you happen to know that you're taking a lot of statistics, if this is just your introductory class, but you know you're going into something, say, biology related, maybe something engineering related, and so on, you're probably going to take more statistics, and the chances are you're going to use this program. It's called R. That's it. That's kind of a weird name, but it's an open source program for statistical computing that's used all over the place these days. Let's just put this back into our plot here. So we've said kind of compromising, going slightly higher at sample size n equals, this was 200. Let me just double check there. Yeah, at sample size 200, the sampling distribution, here it is approximately normal. We have approximate normality. So we could draw a curve to it if we'd like, just like before. But notice once again, this would be at n 0.93. The next part of the notes are discovering what is the variability, what is the spread, or in other words, standard deviation of this distribution. Well, 0.93 is right about here where the main peak is. So this is kind of strange in a sense. Again, any study that's run, whether you're getting a p-hat value, a sample's proportion of successes, or sample mean value, we've done a lot of those. There's another distribution for the sampling distribution of the statistic. P-hat would have came from somewhere here in this situation. So that's going to be the central limit theorem next. This is the simulation part of the notes where we can't ask these questions again on exams and such. But they do come up a little bit on MyLab Statistics, where they'll show you the histograms already pre-made. You have to just decide, is the sample size large enough for the normal distribution to be used? In other words, do you have a large enough sample to use this humongous idea in statistics, the central limit theorem? There's multiple versions of this thing. We'll look into one version for proportions, and the last part of class we'll look into another version for means, averages. And it's a pretty bizarre statement. This is something that can be proven mathematically. So it's a true mathematical theorem. Yet the proof of this thing is gigantic. An entire tome, a book, could be devoted into proving this fact right here. It's nice that we can see it through a simulation, so it looks like something that's highly plausible. It tells us the statistic p-hat comes from a distribution that looks like this. When we say the mean of the distribution, we just mean the center here. And that feels weird because mean is being conflated with proportion. So this is a model that says where the proportion came from, the sample proportion. When we say the mean of the distribution, we're just talking about the center of that normal model. The standard deviation can be written in this way, S for standard, D for deviation. And when it says parenthesis p hat, this is just read as the standard deviation. The parentheses are just a literal of p hat. So there's no multiplication here. This is all just one big symbol to describe how spread out this is. So going up to this point, about right there approximately, this is going to be P plus the standard deviation of P hat. And that's what goes in here, standard deviation, P hat. So this really gives chapter 5 a lot of purpose. The major reason we did all this work with a normal model in section 5.4 is because it comes back in the most bizarre way with even categorical data, and same when we're studying Y-bar. The normal model is just something that's intrinsic about these kind of populations. So these are the two major parts. We can describe the mean, we can even describe the standard deviation, and we'll look in more to rule 3 on example 3 on what do we mean by n large and not too near 0 or 1. So here's example 2 again, just looking at it from a different point of view. We're making a new assumption. We're assuming we don't know what P is. We're just going to admit that. But we're going to say the sample size in this study was 100 participants. So N is equal to 100. 56% participating in the study said it was not okay to friend his or her boss. So that tells us that P hat in this problem, let me use a different color since the color coding has a different meaning here. P hat is 0.56. One thing I should mention right away is writing these down is a good idea because they all feed back into formulas. Another thing that's going to be really major, especially in example 3 and the next part of the notes, is always write as a decimal. If we put the percentage into the formulas, we would get the wrong values out. So I'll try to maintain that as well as we go through the notes. Now, next is part A. Part A turns out to be one of the trickiest parts of this entire thing that we're going to be doing in chapter 13, 14, and 15. Describing an unknown parameter actually isn't easy. We're doing two things at the same exact time. And whether it's categorical data dealing with P or quantitative data dealing with mu, gives you a different process, a different way of dealing with it. But this is extremely important in part A because when we go to give a conclusion at the very end of what we'll call a confidence interval in chapter 13, or a hypothesis test in chapter 14, our conclusion depends entirely on what you put down here. So getting conclusion right means you know exactly what the parameter is. Because that concept is so important, let's write out kind of a sort of a structure, kind of like when we were interpreting the slope. It helps to have a structure. And here's the structure for the unknown parameter P. I often say unknown, just as a reminder, this is not a value we actually can put a number to. It's not 0.56. At best, it's approximately equal to, but it could be way off. Yet, this is how P is going to be described every single time this comes up, and it'll come up a lot. P is going to be equal to, let me make sure I have enough space here, the population proportion of, let's put a blank here to carry out the structure. So far, not so bad in a certain sense. It's always going to say, if you're dealing with P, you're dealing with a proportion. It's a parameter, so it describes a population. But what goes in this first blank is the successes in context. So we have to say what the successes are in each problem. This one's a pretty short context, so it's not so bad, but sometimes they do get kind of wordy and a little bit heavy. We have to say, what is this study all about? That's going to be the successes, and we have to say what it is. So the population proportion of successes for all, this is the second part of getting the parameter down. Another big blank. This is where it would end. All is kind of a giveaway. And because we're dealing with the population, we have to say right here what the population is. In the context. So every single time we go to write down what P is, it's always going to be this structure. Let's actually use that down below. So I have to say what the successes are. Let me blank that out. We have to say what the population is. In some problems, it's pretty straightforward, but keep in mind, in plenty of problems, this is pretty tricky. So we'll always make a big deal out of part A because we're thinking ahead. What is the conclusion even going to look like by being really careful in part A? If we do this just right, our conclusion is almost automatic. So looking into the context once again, the article reported 56% of people participating in a survey of social network users said it was not okay to friend his or her boss. This right here is the success. Because that is the thing that we want to study. So when we come down here, we have to say the population proportion of people that said it is, I'm going to start over just to make sure I can fit it in this line. Population proportion of people that said it's not okay to friend the boss barely fit. I should have made that line a little bit longer. Then we'd go down here and say what the population is. Well, to get the population, keep in mind, the sample comes from the population itself. It said 56% of people participating in a survey, they're described in the sample, of social network users. This portion right here is referring to the population. So this is the population. Depending on the title, Facebook Etiquette at Work, we might have a more refined population. We might hazard a guess that this is social network users on Facebook specifically. But you know, that was just USA's title here. It was a survey, but that survey was not necessarily conducted by them. Sometimes USA Today just reports on other people's statistical work. So for those kinds of things, you can always just make a judgment call. If you're sure it's for Facebook users, just say it down here. I'm not going to be extremely picky on these things. If you're unsure, you can let the population be a little bit more vague and just say, as they said down here, social network users. That always requires a bit of a judgment call. So I'll say down here, for all social network users on Facebook. But if you left off Facebook part, that would be completely fine in this problem. So we got it, folks. That's the description of the parameter. We'll do a lot of these because, again, anytime we make a conclusion, we have to know exactly what the parameter is. This is often going to be the very first thing you do in a statistical inference problem. And it's a great idea because it kind of just centers us, what is the problem all about? Any questions at all, folks, on deconstructing how to write out the parameter and actually doing it? Okay, next, we're just going down through all the moving parts that we're going to eventually build together to construct the confidence interval. Explaining the meaning of p hat equals 0.56. That's this right here. And the prior problem told us that that was the statistic. So we can say here, p hat equals 0.56 means 56% of the sample said it is not okay to friend their boss. It doesn't say 56% of the population, it's just the actual sample they used, which was 100 participants. So that's us just thinking about the statistic again. Now that you have the parameter down, it's good to think about p hat. And these are not the same. P hat estimates p, but p is a true unknown. So that's the difference. P is saying all social network users. P hat is just a percentage of the actual sample used, the 100 people in this study. Now, next, we're going to make another interesting assumption. P is truly unknown, but just for the sake of actually using the central limit theorem, let's assume that the true proportion P takes on a value 0.53. This will allow us to calculate the standard deviation of the sampling distribution, and we'll round it to 4 decimal places. So we put in a value for P. Now we're going to calculate the standard deviation. This is a pretty new formula, so let me just carry down these two parts. Now let's go to do that next portion. So if the true proportion was 0.53, it's different from the statistic value, but that's typical. It's a mathematical miracle if they're dead on equal, and probably something is going wrong with the data. But P really is 0.53. That means we could calculate the standard deviation of p hat. So let's do this computation right here. What is the standard deviation of the sampling distribution? That's like finding this number right here in the prior problem we were looking at. And it's a computation that goes like this. SD of p hat is telling us this is the width of that normal distribution, the ones we simulated, the one mentioned in the central limit theorem. It's going to be the square root of p times 1 minus p. Formula goes p times q. This is how the book writes it in. But q is just 1 minus p. So I think it's easier on paper to write it in this way. So if p is the true proportion, q is the true proportion of failures. I said that weird. P is the true proportion of successes. By the complement rule, 1 minus p, q is the true proportion of failures. We divide this by the sample size n, but we said above n is 100, so we'll carry that in. So this is all we need to calculate. Really, part C is just a practice run on how you would calculate something like this. Writing this down on paper, it's going to be 0.53 times 1 minus 0.53 divide by n, which was 100 that we looked up above. We have to put this into the calculator, round it to 4 decimal places. And this would be the width of that normal distribution. So let's give this a try. Word awarding, we have to calculate a lot of these, and it's actually a slightly tricky computation. There's a couple strategies, so we'll focus on a couple strategies when we do this in class. But here's one good strategy. Let's just work outside in. I'm going to type it like we see on paper, almost verbatim. Start with the square root symbol, hit the second button, and the power 2 button here, kitty cornering up and left from 7. It constructs the square root. And I'm going to carry in the whole numerator, 0.53 times 1 minus 0.53 This we can just type in as a literal division bar. And there's no order of operation issue here because there's no plus or minus in the middle on this one. So order of operations doesn't get messed up. You can hit division 100 just like that. And this is what it would look like in the calculator. I want to screenshot this just so that if you're typing it into the calculator, you have a reference of what should it look like. Then I thought I hit enter, hang on. Well, I did something weird on the calculator, hang on. It went away. Let me try to type it in one more time. Second square root, 0.53, 1 minus 0.53, divide by 100. Hopefully it works this time. Hit enter, and this is what I got. To 4 decimal places, this is a 0.0499.
Your 100, that was just a assumption, right?
Yeah, that came from the value n, and they just said right here, assume the sample size is the 100 participants. Absolutely. Other questions so far? It would get a slightly different number. This turns into be a tricky computation. Okay, just for a slightly different version, if you'd like to calculate it different, you might be an order of operations kind of person, and that works too. Work inside out. You can go 1 minus 0.53, multiply that by 0.53, divided by 100, division 100, then take this, take the square root of the answer, go second, power 2, up arrow and enter so you don't have to retype it, and hit enter again. You'll get the same exact number. So my suggestion is just find a process that makes the most sense to you, that you feel the most comfortable with, stick with it, and you'll be highly accurate when you have to do it again, say, on MyLab statistics, where they're kind of a bully with the numbers coming out just right, or in quizzes and exams. But for the keen-eyed person thinking about everything we've done so far, you should almost never be able to calculate this quantity right here because it depended on a value for P. Now we've said all along from the very first day of class, in statistics, P is an unknown. So we're going to calculate something slightly different. If you can't calculate the standard deviation, what we'll calculate when we come back next class is the so-called standard error. We'll put in the next best thing, p hat. That's something that we do have. That's something the study gave us. We'll see how it goes on in a fresh problem. When we go to calculate the standard error p hat, we're like one step away of giving the entire confidence interval. So we're just about there. We'll use the normal distribution again. The next section is going to give us ideas of when p is not too close to 0 and 1, how large the sample size n is going to be. But for the moment, this is the major takeaway. Our statistic p hat comes from the normal distribution. We're just studying features about that distribution. Any questions or comments at the moment with what we've calculated so far? Okay, so inferential statistics are pretty weird stuff. I think section 13.1 is the weirdest section in this entire book for the entire class. Lots of things happen in this section. But if you're comfortable doing a formula like this, you're going to do great with the confidence interval. The hardest thing is going to be nailing down P. But we've been practicing all semester. That's why you've seen so many problems. I kept on saying, use the context. Because if you get comfortable with context, writing down P is not as bad. But have a great night, folks. We'll be right back on these notes on Wednesday's class, moving into the very next section.
I ask you a question?
Yeah, absolutely.
Quiz?
Yeah,
Well, this has some crazy numbers, but I checked it on the calculator with that. And it got that, so it's gotta be right, right?
absolutely. Yeah, that's an excellent check.
Um. My. So does it make sense to interpret the y-intercept? So that's where it's gonna intercept here when this is at 0.
Yeah. So that'd be the age of the Corvette years is now set to 0, so brand new Corvette.
So even though it's not 1 year. I mean, I would say that you could still interpret that.
I agree, yeah.
Okay.
It's not like in other problems where 0 meant someone's not breathing or something weird like that. It's close to the data too, because there are 1-year Corvettes in this data set. So yeah, it definitely makes sense. It's just gonna be the Kelly book value of
Of a
a
brand new
brand
car.
new one, yeah.
And then give a practical interpretation for the slope. See how we solve this tonight?
Yeah.
So I wrote this little formula down,
Mhm.
and I literally just plug in the year, the age of the car,
Yeah,
and the price
exactly.
will increase by,
Well, it's either gonna be an increase or decrease. It'll be decrease for you because you've got a negative on your slope.
if it's a negative,
Yeah, you're losing value like crazy on this car.
oh, I put increase or decrease in my notes.
Oh, awesome, good call.
But I can just plug, I mean, that's what you're looking for,
Exactly.
is that sentence
Mhm.
with those things plugged in there?
Exactly, that structure is gonna work on every single one of those. That's kind of like this parameter P stuff that we just wrote down.
Yeah,
Every time that comes up, that's the structure that'll work each and every time.
perfect. And one last question, just
Yeah.
because it's not on this question. Calculating the residual.
Oh, yeah, that's right. So a residual question might ask you for something like, let's see, for 2 years old, what is the residual for a Corvette that's 2 years old? You would take the observed value, 425,000.
Oh, that was it, minus the y-intercept, right? Y minus y hat.
That'd be the predicted value. That'd be the value that you computed in part B, the Y hat value, that 410,747.
Oh, that's the one that I want,
Yeah,
for the residual,
exactly. So you take,
425
yeah,
minus that,
exactly,
and that would be the residual.
exactly.
Okay. Yeah,
Which means your residual on this one is going to be negative. And so our line is actually overestimating the value of this Corvette. So the true value is 425,000. Hang on, let me double check that thought here. No, I think I got that backwards. So the observed was 425,000, predicted it is 410,000. Our residual is going to come out as positive, which means the actual value that we predicted is low volume, the real value of those cars. So we're kind of on the low end.
okay. So would I could just put that in dollar amounts, right? But do I need to put a, parameter by it?
No, you wouldn't have to.
Okay,
Yeah, that'd be a great answer for that one.
perfect. That's sweet. I'll print it out and give you a photo.
Awesome.
Cool, thank you.
You bet.
It's not as bad as I made it out the other day, huh?
No, well, learning it for the first time, it really is, because you've got like 12 different concepts you're looking at all at once. But bit by bit, part by part, that's not so bad, I agree.
Think sometimes too, sometimes you just gotta walk away, you know? Come
Yeah,
back another day.
absolutely. Yeah, you never underestimate the value of a mental break with this kind of stuff.
How many pages will we get for the final exam?
It's gonna be
No.
2 pages.
2?
Yeah, so we're gonna have to do some condensing, but you'll have a pretty good idea of what's gonna go on there by that point.
Yeah,
So 2 pages, front and back, that's quite a lot of real estate.
it is, especially with technology, you know?
Yeah, cause you can shrink things down if you're clever with it.
Yeah,
It can be handwritten, printed out, so,
well, you can take your, you know how you do your screenshots?
Yeah.
So you can do that.
absolutely, you can do it with your own notes,
Your
stuff
notes.
that you've had returned to you graded, my notes up here, with anything whatsoever. The textbook itself, if you wanted to,
Yeah,
anything's fair game.
that makes it pretty doable.
Yeah, but that's what statistics is all about, just doing the research ahead of the time. So you know what you need to solve a problem. It's kind of what we're doing on the final exam.
I know it's getting a little trickier, but I was waiting for it.
Yeah,
The first couple weeks, I was like, man, this is gonna be a cakewalk, but no, I better. Bye.
it won't be too bad though.
But, have a good, Monday.
Yep, see ya.